Hello guys, welcome to Ramta Solutions. Welcome to your grade 10 physical sciences video on electrostatics. This is a full guide of the topic, and so when you are done watching this video, you should be confident to attempt past papers on this topic. Okay, cool. Now we're going to begin with an introduction on electrostatics, telling you what it's about and everything there is to know prior in proceeding or getting into the most technical information. Then we're going to look at the kinds of charges that we have, proceeding to the law of conservation of charge, and then concluding the video with quantization of charge. We will try our level best to give examples where possible. So, without any waste of time, let's get into it. Now, if you did not know, now you know. We are all made up of electric charges, right? And I want to give you an example. If you have ever heard an expression, somebody is electric, where they say, wherever you get, people are attracted to you. Right? So, you know such people, right? Wherever they are, everybody welcomes them. And of course, God forbid, there are those who you don't even know why people dislike you. But it happens to each and every one of us. Even that person who's electric, there are people that dislike them, right? And that is basically charges. And you can imagine these charges, they do not need to be in contact. So that tells you there is some force that objects exert on each other. So, okay, let's come back to our lesson. So, yes, we are all made up of electric charges. So, and so is everything around us. Everything around us is made up of electric charges. There is an attraction or repulsion of objects, all right? Now, the topic that we are dealing with today is electrostatics. If I were to ask you what your thoughts are on electrostatics, what would you say? Well, I would say to you, think about it in this way. This word electrostatics is made up of two words, one word being electro and the other being static. Right? Electro somehow must be something to do with electricity or electric charge. Statics must be something to do with motion. If you remember statics, if something is static, we know that it is not moving. So, electrostatics, electric charge and not moving. Well, let's give the definition. Electrostatics is the study of electric charge, which is at rest. Or if you don't want to say at rest, you can say which is static. Happy? Oh yeah. Now, we talk in charges. Charge or a charge is a scalar quantity, right? A charge is a scalar quantity, right? And it being a scalar quantity, it is measured in the units coulomb with a symbol C. Okay, coulomb with a symbol C. Okay, coulomb with a symbol C. All right, so this is all you need to know. And please note, electrostatics has a huge application in industry, but we're not going to talk about that today. You're going to see some of them. Okay, so stay tuned. Now, there are two types of charges, and what are those charges? It is a positive charge and a negative charge. And however, we must say there's also a neutral charge. Okay, now what is a positive charge? This is a charge carried by protons. What does it mean? It means that a positive charge is basically a charged object which has more protons. All right. And then what is a negative charge? This is a charge or an object that is carried by electrons. So this object, it means it has more, it means it has what? It means it has more electrons than protons. So, as you know, objects carry both protons and electrons. Okay? With a positive charge, they have more protons, meaning few electrons. With a negative charge, it has more electrons and few protons. All right? All right. Now, let's look at these objects. I want you to imagine this. When you see the plus, you are seeing a proton. When you're seeing the negative, you are seeing an electron. So let's count the number of protons for this first sphere. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's look at the electrons. 1, 2, 3, 4, 5, 6, 7. I'm going to say minus, okay? So what is the net charge? The net charge will be positive 2. Okay, we will come back. Let's look at this one here. Let's look at the protons. 1, 2, 3, 4, 5, 6, 7. Let's look at the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 9. What is the net charge here? The net charge is negative 2. Let's look at this one now. This one, 1, 2, 3, 4, 5, 6, 7. We have 7 protons. Let's look at electrons. 1, 2, 3, 4, 5, 6, 7. Ooh, what is the net charge here? It's 0. Right? It is 0. Now, positive charge. What did we say about a positive charge? We said it is carried by protons. Now, what you can see with this diagram here is that electrons are being removed. However, I don't want to say electrons are being removed as yet. I want to say it has fewer electrons. Okay, it has fewer electrons. So a positive charge is electron deficient. But of course, for a positive charge, electrons are removed. Okay, for a positive charge, electrons are removed. Now, let's look at the object in the middle. What is it? Ooh, I saw the net charge is negative. So what is this? This is a negative charge. So what is happening with a negative charge? Electrons are being added. This means it has more electrons. So what do we say about it? This object has excess electrons, isn't it? Has excess electrons. Now, the third one, we say it's a neutral charge. Why? Because protons and electrons have the same numbers, right? They are equal. So it has the same number of positive and negative charges, isn't it? This is a neutral object or a neutral charge. Okay, perfect. Now, we are going to look at triboelectric charging. Now, this you see a lot with the rubbing of objects. Imagine that ruler that you just bought now. Say you cut piece of papers. When you cut piece of papers, if you were to place the ruler above the paper, they won't be attracted to the ruler, so they won't move, right? But after rubbing the ruler, say, against your hair or your t-shirt, there's somehow an attraction. And this is what we are talking about. Remember, this is what you did in grade 9. So, yes, by triboelectric charging, this is where objects are charged by other objects. Okay, objects are charged by other objects. Okay, and there is a list of materials that show you how or which objects will be charged by which other object. Okay, So in other words, when you look at the list, it's going to show, just now, just hold. When you look at the list, it shows you different materials and their ability to be charged. Okay, so look at this series. This is a triboelectric charging series. Okay, the list, of course, here it is a few materials, but there can be a list of so many materials. Okay, but for now we're going to use this one here. So with this list here, I want you to know this. We're saying as you go down, the material becomes less negative, meaning the material, as you go down the series, the material is the one that's likely to be negative when contacted with the material above it. For example, rubbing glass with PVC, the PVC material will be more negative because the glass will be positive. So what does that mean? That means the glass is the one that will lose electrons, while the PVC is the one that will gain electrons. So it will be more negative, whereas the glass will be more positive. Okay? All right. So yes, more positive materials will lose electrons. This is is the reality that we know. However, we couldn't explain it until now. And this is why you are doing physical sciences. All right? Perfect. Now, you need to ask yourself, but man, how are these charges transferred? I'm gonna give you an example here. You remember, okay. So in our diagram here, let me add, let me add some charges here. So let me add them. Perhaps let me add. I'm just gonna make them 6. Okay. Yeah, let me add them, and here let me add another one here. Okay. And even here, let me add another one. Yeah. Okay. Yeah. Let me do this. So you remember I spoke about rubbing a ruler against your hair and then trying to see if the piece of papers will be attached. All right. So now let me show you now. Let's say before you rub your ruler, look at it now. Here is your ruler. How many positive charges does it have? It has 6 positive or 6 protons and then 6 electrons. And look at this is the cotton. Let's call it a cotton. It has 4 protons and 4 electrons. All right. Now, as you can see, are these are what? These are neutral, right? As you can see, the net is 0. Can you see that? Their net charge is 0. When I say net, I mean sum of the proton plus sum of the electrons. It will be 0, isn't it? Good. Now, when you look at PVC, we can classify it as a plastic, and then cotton, here is it. What you are expecting cotton on rubbing with PVC, for example, the ruler, you're expecting the cotton to lose electrons. All right, you're expecting the cotton to lose electrons. Now let's see what's going to happen. So look at this now. Let's keep drawing. So how many charges do we have? Protons, 2, 4, 6. We have 6. And then how many electrons? 2, 4, 6, 8. We have 8, right? And for the cotton, how many do we have protons? We have 4 protons. How many electrons? We have 2 electrons, right? Now, when you look at this, indeed, according to the tribal electric charging series, it makes sense that the cotton will lose electrons, whereas the ruler will be getting more negative, meaning it gains electrons. Can you see that? At first, the ruler had 6 electrons, but now it has 8. At first, the cotton had 4 electrons. Now it has -2. All right. So if you are to look at this, let's say now we look at the what is this? We're looking at the net charge of our objects before rubbing and after rubbing. You will realize that they are the same. All right. You will realize that they are the same. Right. So let's look at this. The total positive charges, or the total protons before rubbing was 6 plus 4, which is um 10, and after rubbing, again 6 minus 4, which is 10. Again, it's 10. What is the net? What is the net? The net is 0. All right. And then let's look at the final. I'm going to say final. The net charge. Ooh, I don't know why I said E. I don't know why I'm saying E. I really don't know why I'm saying E. I'm going to change it to Q. Okay. I'm going to change it to Q. Okay. I'm going to change it to Q. Final charge net. Yeah, net final charge will be how many protons? We have 10 again. Check this out. 6 plus 4. 6 plus 4 is 10. And then 10 minus 2 is, or rather 8 plus 2 is 10. Again, this is 0, isn't it? This is 0. Right? This is 0. So as you can see, here we are saying, oh, so the total charge before rubbing is equal to the total charge after rubbing. When you look at this system, the system before rubbing, 4 6 4 6 4, right? After rubbing, 6 4 8 2. But when you look at the net, it'll still give you exactly what you had, right? This is giving rise to what? It is giving rise to your conservation of charge, which you're going to see shortly. Okay. All right. Now, as you have seen, we did say that the most positive on the triboelectric series will lose electrons, right? And this was the case. I showed you that the cotton was appearing up in the series and the PVC, or the plastic, was appearing at the bottom, right? Good. Proceeding. Now let's talk about the forces between charges. Guys, though these charges are static, not moving, they exert charges on each other. And if you remember, last year you spoke of types of forces. You spoke of contact forces and non-contact forces, right? You spoke about them. So now you're looking at contact forces. So now when you look at these guys, since they are not moving, but there is some form of attraction, these will become non-contact forces. All right. So these objects, or charges, rather stationary charges, exert forces on each other. And that force, we term it what? An electrostatic force. Okay? We call it an electrostatic force. Okay? Good. Now, this electrostatic force can be attractive or repulsive. When is it attractive? When you are contacting opposite charges or oppositely charged objects. Okay? When you are contacting opposite charges, okay, you can say opposite or unlike. This is when a positive charge is contacted with a negative charge. And then when are they repulsive? When you are contacting like charges. Like charges is when you say opposite charge contacting it with another opposite charge, or a negative charge contacting it with a negative charge. This is when you will experience a repulsive force. But if you contact objects with opposite charges, you will experience an attractive electrostatic force. Okay, good. Now, another thing is this one here. The closer the objects are, the stronger the electrostatic force between them. Okay, the stronger the electrostatic force between them. I think let me change the color. The stronger the electrostatic force between them. So think about it in this way. The strength of the electrostatic force has nothing to do with whether the force is attractive or repulsive. You can have a strong repulsive force, you can have a weak repulsive force, You can have a strong attractive force. You can have a weak attractive force. Okay. Now, let's check this one. Let's imagine the distance between two objects. Let's say this is positive charge and this is negative charge. So obviously they will be attracted because they are opposite of charges, right? And let's imagine this one here. Look at the distance. Okay, look at the distance and look at this one here. Oops, let me make it a negative force. So what is this? When you look at this, these will be strong. Why? Because as objects are closer to each other, they will have a stronger electrostatic force. When they are far apart, they will have a weaker electrostatic force. So this is a stronger attractive force, isn't it? This one is a stronger attractive force, and this one here is a weaker attractive force, isn't it? And this one here is a weaker attractive force. All right. Now let's imagine now for repulsive forces. I'm gonna try with uh, negative and negative when they repel each other. Okay. Do you see this? So this will be a stronger now compared with this one here. So you see the distance again, negative and negative. So this will be a weaker repulsive force, whereas this one will be a stronger repulsive force. Maybe even if you had drawn it way closer, maybe it could have been better. The illustration would have been better. Now let me do this. You see? So this will be a weaker repulsive force, and this will be a stronger repulsive force, and this will be a weaker repulsive force. Okay? Remember, the closer the objects are, the stronger the electrostatic force between them. Okay? Now, let's look at polarization. You wondering, we said there is an attraction only when a positive and a negative object um, are brought together, right? But now you can also get attraction when a charged object is placed near a neutral object, and that is what we call polarization. Okay, so in simple terms, you should think of it in this way. You should think of it in this way, where we're looking at when a charged object exerts a force on a neutral insulator. Remember insulator? We will talk about them shortly. Okay, I will talk about it shortly. Okay, so now I want to say this: when a charged object attracts a neutral object, this is when you experience polarization. Okay, this is when you experience polarization. Okay, all right. Then we will talk about the conservation of charge. In physical sciences, whenever you see conservation, I want you to imagine this. The net of a property before is equal to the net of a property after. Or you can say the net of a property in an isolated system remains the same. Those are the laws of physics. Whenever you hear conservation, you must always think, oh, it means the total of whatever property before is equal to the total of that property after. Or in an isolated system, the total of that property remains constant. Just like that. So the conservation of charge, we can say, look at this. Net charge, total. Net is similar to total. So we are saying the net charge of an isolated system remains constant during any physical process. See, this is how you will always define conservation of whatever in physical sciences. You say the net property could be momentum. If there's conservation of force, you say the net force. If there's conservation of mass, you say the net mass. You see things like that. So now when they say conservation of, You say the net blah blah of an isolated system remains constant. That's it. You only change this part after of. If it's conservation of momentum, you'll be saying net momentum of an isolated system remains constant. If it's mass, net mass of an isolated system remains constant. You see, just like that. Okay. So now, because we're talking conservation of charge, we will say the net charge of an isolated system remains constant during any physical process. Or what everybody likes, electric charge cannot be created or destroyed. Okay, it cannot be created nor destroyed. This is what everybody likes, and this is what, in fact, everybody's used to. Okay, so this is it. This is the law of conservation of charge. And I showed you with that example of the net charge of the ruler and the cotton. You saw it, right? Uh-huh. Now, we have different materials that allow electrons to flow through. One that really allows electrons to flow through or to move through them is what we call a conductor. Now, a conductor, examples of our conductors are metals. You're gonna see some examples later. Okay, so conductors, they allow electrons to move freely through them. Okay, and then we have insulators, which are non-conductors. These do not allow electrons to flow through them. Okay, they do not allow electrons to flow through them. Examples are your plastics, right? Examples are your, even I think saying plastics might be, but yeah, plastics, for examples, they don't allow electrons to flow through them. Okay, most non-metals, they don't allow electricity to flow through them or electrons to flow through them. Okay, so yes, these are examples: non-metals, rubber, and plastics. Right now, we have another material which we will call a semiconductor. A semiconductor, this one has properties, somehow we're going to call them intermediate, but exhibits properties of a conductor and of a non-conductor, right? Non-conductor, remember, we call them insulators, right? It has those properties. So it's not that it's fully conducting, and it's not that it's not fully non-conducting. It conducts to some extent. It's not conducting to some extent. You get it? Now let's look at examples of these materials. For your insulators, dry air, dry wood, rubber, and glass. And your semiconductors, you have your silicon, germanium, seawater. What about your conductors? As you can see, it's metal, silver, copper, aluminum, iron, mercury, carbon. Right? So these are some of the example of your materials. Okay? All right. Now, again, we know that an electrostatic force basically gives an arrangement of charges on the surface of a conductor, where sometimes you can find, let's say this is an object, electrons could be distributed like this. Do you see these ones are so close together? And sometimes they can be like this. You see that? They can be like this. So these are equally spaced. All right. Your force has this ability. All right. Now, this is not the only thing. Now, let's imagine now how these charges can also be spread. So now let's imagine now two spheres being brought into contact. Okay. It doesn't matter whether they are attractive or repulsive. They are being brought into contact and then separated. Right? So if they are being brought into contact and then separated, of course, this can only happen with, or this can happen with unlike charges, isn't it? This can happen with unlike charges or opposite charges, right? Because they can really be brought into contact, right? Now, When this happens, imagine now you bring them together and then you separate them. Now, what happens later? You remember the most positive, what will it do? It'll lose electrons, right? The most positive will lose electrons, right? And now, what happens when it loses electrons? Both charges will then have equal charges, okay? And for that, we use this formula. So charge of each sphere after being brought into contact and separated will be the average of the two charges. This is the average of the two charges, okay? This is the average of the two charges, okay? All right. So I do need to tell you guys, this can also apply for like charges. It's not only applying for unlike charges, it can also apply for like charges. They can be brought together and separated, of course. Okay, now let's see. Example 1 or example says sphere 1 and sphere 2 have charges 8 microcoulombs and 4 microcoulombs respectively. What is the charge of the spheres if they are brought into contact and then separated? So we don't have to stress. You remember the formula? Charge is equal to charge of sphere 1 plus charge of sphere 2 all over 2. What is the charge of sphere 1? It is negative 8 microcoulomb. I write it as it is. What is the charge of sphere 2? It is positive 4 microcoulombs. All right? Negative 8 plus 4 is negative 4. Negative 4 over 2 will be negative 2 microcoulomb. So, sphere 1 and sphere 2 will each have negative 2 microcoulombs after being brought into contact and being separated. Upon separation, each of them now carry this charge. Okay? Upon separation, each of them now carry this charge. Okay? Perfect. Then, lastly, we look at the quantization of charge. So we use this equation. You know now that this Q represents the charge. We said that in the opening slide. It represents the charge. And what is this N and Q sub E? This N represents the number of electrons transferred. Remember, electrons, how they are transferred. They can be added. When they are added, this is when you have a negative charge. When they are removed, this is when you have a positive charge. Remember, for a negative charge, it has excess electrons. For a positive charge, it has deficit electrons or deficit of electrons. All right? So this N is the number of electrons transferred. And this Q sub E is the elementary charge. That is charge of an electron. It is basically negative 1,6 times 10 to the negative 19. If you're referring to a proton, it will be positive 1,6 times 10 to the negative 19 coulombs. Okay, this equation is very important. And by the way, it is given in your data sheet. Okay, it is given in your data sheet. Okay, and so is the elementary charge. It's also given in your data sheet. In case you forget them, it is given. Now, let's see now. An object has an excess charge of negative 1. Ooh, excess. It means it has more electrons. So, hence, it is not surprising that the charge is negative. All right? Negative 1,92 times 10 to the negative 17 coulombs. How many excess electrons does it have? You remember the formula. Q equals small n times small q sub e. What is this Q? It is negative 1,92 times 10 to the negative 17. What is the n? We do not know. We said charge of an electron is 1,6 times 10 to the negative 19. Now let's take out our calculators. 1,92 times 10 to the negative 17 over 1,6 times 10 to the negative 19. What does it mean? It therefore means that the number of electrons are 120. So when you have a charge of negative 1,92 times 10 to the negative 17, you have 120 electrons that are taking part in the transfer of electrons. So this object has 120 electrons in excess. Okay, it has 120 electrons in excess. So we have come to the end of our video. Remember, if you would like to get in touch with us, visit our website www.ramtasolutions.co.za, or you are probably watching on YouTube. You can visit us on any of these social media platforms. Okay, you can visit us on any of these icons. The links to these platforms are given in the description of the video. And of course, if you would like to talk to us, you can also WhatsApp us. We are available on WhatsApp as well. Okay, we are also available on WhatsApp. So with that being said, let us say Realibucha, Siabonga, thank you, and Asante. Bye bye.